right? And there's ways of learning support vector machines in that situation, uses what's called slack variables. For those of you that take a machine learning class, you'll learn a whole lot more about how SVMs and slack variables work. But basically what it does is it says, let me try to find the maximum margin possible, allowing for the fact that some of my points are going to end up on the wrong side. Okay? So that's how you handle that. So even if you have this great big long feature vector, if things aren't totally linear separable, you're okay. So that's when you have a large input feature vector, often it's the case that people use linear SVMs. So here's another kernel, okay, that people use, and it's very common to use, and it's a Gaussian kernel, sometimes called RBF, radial basis function. So it's a kernel where just as point moves away from the support vector, you know, xj moves away from xi, it just falls off like a Gaussian, so it's like a Gaussian bump. Now, you might wonder, I did, how is that exactly a kernel? Well, and also, because that means that there's some space in which this exponential is a dot product, okay? And I realized I had learned this before and I had forgotten it, that the dimensionality of that space is essentially infinite. And there are a couple of ways of thinking about this, but the one that's the simplest is, it turns out you can write that exponentiation, or that decaying exponential, this way, okay? So here's my exponential, the sigma's been removed, sigma squared equals 1. And notice, this is just some particular value, so you just, the magnitude of x, this is the magnitude of x dot, so for some x and x dot it's fixed. But notice that you're taking dot products, and you're taking an infinite sum of them. So it's the dot product raised to this j power. Let me remove that, right? So it's the sum of, and these terms come out because they're constant. It's the sum of this dot product raised to the j power, j equal to 0 to infinity. Do you remember that e to the x was an infinite exponential series, right? So way back in Mrs. McGillicuddy's, maybe you didn't learn this in McGillicuddy's algebra class. Maybe you learned in Miss Thompson's calculus class about infinite series, and right, that an exponential e to the x squared was x plus x squared over 2 factorial plus x cubed over 3 factorial, an infinite sum. That's, see the factorial here on the bottom? That's related to the sum that's going on. So the idea is that this Gaussian kernel actually has infinite dimension in its lifting space, but you know what? We don't actually have to do that. We can just use the Gaussian kernel. There's another interesting kernel that's used in computer vision I want to mention explicitly because it worked so much better than what people might have tried originally. Often in computer vision, we'll build histograms of some distribution to describe something. So we'll actually talk about it just a little bit when we talk about video and activity recognition. You might build up what are called a bunch of visual code words. All right, so you find a whole bunch of interest points in video or set, and you say, well, they're all different kinds, but let me create a whole bunch of buckets, maybe 1,000 different buckets, and I'm going to map each one of these points to being into one of those buckets. So if you give me a chunk of video, it could be described by the histogram of how many of each visual code word show up. So I've got two different pieces of video and I want to compare them. I want a similarity metric between these histograms. So people used a variety of things. You can think of them as distributions, so you can use KL divergence or symmetric KL divergence or Bhattacharya distance, which is another way of comparing densities. But Jitendra Malik and his students came up with what's called the histogram intersection kernel. And the histogram intersection kernel is incredibly simple. All right? So your xi's and xj's, they're now the vectors of the histogram. And you just sum up over all of them the min of the two values, right? So in bin 1, whichever one is smaller, you take that. Oh, and by the way, the histogram has been normalized to sum to 1. And if you take that value and you sum them up, you'll realize the minimum value is 0, right? If one bin is empty when the other one is full, I'll always take the empty ones, so that I could sum up all zeros. And the maximum it can be is 1, because if they're all identical, then it doesn't matter which one I pick. and the histogram has been normalized to sum to 1 anyway. So it can have a large number of dimensions if you have, for example, a large number of code words that you're histogramming. And it's very effective and sort of caught people a little bit by surprise, I think, because people had been doing things like Euclidean distances on histogram, which turns out to be a bad idea, and this is just much more effective. So let's just summarize. Using SVMs for, say, recognition, okay? So you have to define your representation. That is, you need some base feature space, right? Some feature vector in which you're representing. So whether you're doing hog or whatever it is. You select a kernel function. I'm not going to tell you at the moment yet how you do that. Given a kernel function, you can compute the kernel between all your inputs, all the xi's and all the xj's. That matrix is what you can then use to find your support vectors. Remember, to find the support vectors, it has to be able to compute the dot product of xi and xj, but in this case we're going to use the kernel of xi and xj because it's the dot product in some space. And what's cool is, you'll notice here that there's a boundary that's not a line. It's a line or hyperplane in some high dimensional space, but back in the original space, the boundary is whatever it is. And in fact, if you use RBF, radial basis functions, you can sort of see it move around your points elegantly. And that's part of what gave the power of SVMs, is that you can essentially bend the surface where you need to near your support vectors. So at training, this is how you do the training. And then at recognition, to classify, it's very simple. You take a new example, you compute the kernel values between it and only the support vectors, multiply by the weights, the alphas, and if it's positive, it's a positive example, negative net, so here it's sort of faces and non-faces. Let me show you one of the earlier examples using this in a way that was kind of intriguing. Magadam and Yang, they did some nice work on gender classification. Okay, so given a face, can you tell me whether it's a man or a woman? That's it. That's the basic thing. And what they were doing is, you can see they were just cropping out sort of the center of the face here. In order to do that, they had some machinery to take this image. I think this is still the old mayor. I think it's Mayor White of Boston a while back, and essentially finds the face, scales it, finds the features, can warp it and straighten it out, and then cut out just the part of the face that they want. Okay, so they can automatically go generate the candidate. They can automatically generate the candidates. All right, so they trained it. Their training examples had about 1,000 men, 700 women, which is a pretty reasonable ratio in academic labs, but really they should have tried to balance it. The images were shrunk down to being only 21 by 12 pixels, okay? So it's a relatively small feature. It's still got whatever 21 times 12 is, let's see, 210 and 42, so 252 numbers, right? But they're not just going to base it on that. They actually used a Gaussian kernel, okay, a Gaussian RBF. So that's defined as xi and xj, and when you compute some new input x against your support vectors, so here is kx, so x is your new input, and the xj is each of the support vectors. So you have to compute this quantity at testing time in order to determine whether it's a man or a woman, okay? What's interesting is, remember we had support vectors, which were actually the points, right? And these are the points that are sort of the harder points, right? They're the ones near the boundary. Well, we still have support vectors, but now you can call these things support faces. Remember eigenfaces? And by the way, Bobick Magadam was a student of Sandy Penland with Matt Turk, the people who did the eigenface, and then Bobick did his own thing on parts of faces and face space. All right. But what you can do is you can now find the support vectors, which in some sense are the faces that are closest to the boundary, right? In some sense, they should, not in some sense, they are the faces that are sort of harder to label, okay? So male versus female. You can see these are pretty similar, right? These are pretty similar. And yet one is male, one is female. Here's another example. Maybe this one's not so hard. So this is just some of the support vectors' faces. What was kind of nice about this is that they trained a variety of classifiers. All right, here they are, some simple nearest neighbor, which you can see down at the bottom, a Fisher linear discriminant, which says, let me try to find a single line that separates things the best, but in the original dimensional space. Then they tried a variety of methods, and what's really cool is the SVM, all right, the support vector machine with the radial basis function, the Gaussian one, only had an error rate of like 3.4%, which is pretty good. In fact, how good is it? Well, you should see how well can humans do on this data set. Because remember, they just cropped the middle of the face. All right? So they did a test with people where they had 30 subjects, 22 male, 8 female. That's also closer to an academic lab typically. And their test data was 254 faces, 60% male, 40% female. I don't know why they wouldn't use 50-50, but that's what they did. They used low-res versions and high-res versions. We'll get to that in a minute. And then the task was, is it male or female? We'll give you all data to decide, but you have to make a choice. You can't say, I don't know, and you can take as long as you want. So that was how well humans could do. If you take a look at how well machines do, okay, the SVMs performs better than any single or it should say than every single subject. In other words, the machine was better than the best person. Okay? And the overall performance, you can see the SVM didn't care at all, really, about the low-res versus the high-res. In fact, it had slightly higher error rates on the high resolution than low, which, and you know, it could be that that difference is not statistically significant. Unsurprisingly, the humans did much better at the high resolution. Remember, we saw it was 6%, and the low resolution, you know, they did awful. So the machine did better than the humans. This is something we see a lot. If you have lots of data to train, the machine learning methods can be quite sensitive to learning the distinctions, sometimes better than what humans can do. The one thing you have to be a little careful of in this particular thing is, remember that low resolution image I showed you? I went back and I read the paper. On the left is the original 48 by 84 image, okay? In the middle is the 12 by 21 image that they showed, but of course it's blown up to be the same size. And when you blow it up to be the same size, you put these edges in here. Now, we talked about this, right? What happens if you just replicate the pixels? Remember aliasing? What you've done is you've put in these high-frequency things that really don't belong there. If you were to smooth that image, you would remove that aliased stuff, or you could reconstruct it better, you'd get a picture that looks like this. And I'm going to guess that this picture would have been easier for humans to deal with than this picture, even though they have exactly the same amount of information, right? This picture is just the blurred version of that one, okay? So that's something to remember. In fact, let's do a quick psychophysics experiment. You ready? All right. Can you recognize that picture? Say no.
No.
Okay. I'm going to take that same picture, and now I'm just going to blur it. Can you recognize it now? Do you remember the picture? Come here, come here, come here, come here. I'm going to make you get on camera, on camera, on camera. There you go. So who is that?
That's you.
That's your hero, you're supposed to say.
That's my hero.
There you go. Yes, that ugly puss is me. Now, you know, when you were looking at just this picture, that was probably hard to tell. So you have to be a little careful on how you do things and, you know, for your psychophysics. So that ends that digression. By the way, here were the hardest examples for humans to classify. Okay? So you might take a look at them and try to decide what you think they are. I'm not going to do that because I don't know who they are and I don't want to insult anybody. These were the actual true examples. The true labels. So did you get them right? I got one wrong. I'm not going to tell you which. All right, last question. Remember we said features are not 2D, no problem, just hyperplanes. If the labels are not linearly separable, we do this really cool thing with the kernel trick, and that puts us in a higher dimensional space, and we separate them up there. Well, what if we have we don't have just two categories? What if we have more than two? Well, you have a couple of choices, none of which are particularly satisfying. Basically, SVMs allow you to create binary classifiers, this versus that. The simplest thing you can do, well, not the simplest, one thing you can do is you can train, it's called one versus all. You can train the A's versus not A's. right? And the B's versus not B's, and the C's, you get the point, right? And then at testing time, you apply all of these machines, and you assign it to the SVM that is, it's actually interesting, we haven't talked about this.